So welcome everyone to this week's Stochastics and Statistics seminar. It's my great pleasure to welcome Thibaut Gouic, who's been visiting MIT for the past 2 years now almost. Before that, he was at HSE Moscow as a visitor as well. So he's a traveling mathematician, and but he's originally from École Centrale Marseille. Thibaut is a specialist on the interaction of statistics and geometry, and in particular in the context of the geometry of the Wasserstein space. So if you're familiar with his work, you're probably familiar with his work with Boissard on rates of convergence of the empirical measure to the true measure and Wasserstein distance, which is a classic. And he also has a pretty popular work on template deformation models. Where, again, optimal transport plays a key role. So today is going to talk about various questions related to barycenters in the Wasserstein space, where we will see a display of all his expertise. Take it away, Thibaut.
Okay, thank you, Philippe. Thank you for the nice introduction, and thank you for inviting me for this seminar. I'm really happy to talk here. So today I want to talk about barycenters in Wasserstein spaces, and I will start with the notion that barycenters is capturing, which is averaging in some particular spaces. So the notion of averaging or taking average is a notion that has been used by scientists for centuries to try to take into account errors of measurements and to reduce these accounts. I think the first time it was used was as a scientist or by an astronomer in this context to reduce errors of measurements, but like in the 16th century, where this astronomer would measure at the direction at which some star would rise every time it would rise, and take the average to take into account the error of parallax and refraction. And so nowadays we are starting to have data that are more complex, and taking average requires more work. There is, for example, this set of faces where people are taking average of this set of faces, and from different notions of averaging that you can find. And depending on the notion of averaging you can find, and depending on the spaces under which your data point here, the faces, lives, you have different kind of properties for your average, for your notion of average. And this is the purpose or the point of this talk. I want to talk about influence or the impact of the geometrical aspects of the underlying structure, where the data point lies, on the statistical property of this notion of average, and on the computational properties of this notion of average. So I will start with some drawings so that things are more intuitive, and this is also how I like to think, with some drawings in my head. So it's easier for me to explain the things that way. So the first notion of average is the one that we have on the Euclidean space. And it's pretty simple. I have a bunch of points that are my data point, my data set. And I want to sum up these points by one point that would be in the center or in the middle of all these points. And to that purpose, I take the average. There is a very simple formula in the Euclidean space, which is this one. And from this formula, I can compute the average. The one key point of this formula, it relies on the linear structure of the Euclidean space. So I have a sum, I have a multiplication, and because it relies on this linear structure, it's hard to extend this exact definition on more complex or more on other spaces that don't have this linear structure. For example, on the sphere, we don't have this linear structure, and we cannot define this in the same way. Lucky for us, there is another way to see this definition. It's also the point that is on average the closest, or like that minimizes the square distance to all the data points. So it's a point, let's say A or B, that minimize the square distance between all my data points. And when I have this definition, this formulation, then this formulation just is an average of the square distance, so it makes appear only the distance between the 2 points, between 2 points, and I can extend it to every metric space, including the sphere. So from a point that I have on the sphere, I have this bunch of orange points that I drew here, and I want to define a midpoint, which would be somewhere where this cross, the blue cross that is here is. And I can use this definition, and my barycenter here would be the argmin of also the average of the sum of the square distance to my data point whenever I have a distance on my sphere. So I will use the arc length distance here to define my sphere. Okay, and this definition for a finite set of points can easily be extended. And this gives rise to the definition of barycenter, that is also known as Fréchet mean. And for any probability distribution P, I can define on a metric space. I can define its barycenter by taking the argmin of the average of the square distance to the point of my that are drawn from P. And I will denote by B star this barycenter for a given P. I will also denote this functional that I'm minimizing, the variance functional, and I will write it as sigma square indexed by P, and here is evaluated at P. Okay, so there are two main issues for this definition that we do not have in the Euclidean case. First is that this argmin do not always exist. Lucky for us, the cases where it does not exist are pretty rare. It takes some work to build a space and a measure on the space so that the minimum does not exist. So we'll not be concerned about this, but one thing that will concern us more is that this minimum is not unique. And it's pretty easy to build an example where it's not unique. And we'll again use the sphere as our main example to have our intuition of what's happening. Whenever I take 1 point in the North Pole and 1 point in the South Pole, then I can define my measure as the empirical measure on these 2 points. And whatever point that is in the barycenter, also in the equator of this sphere, is a barycenter of P. So this is pretty easy to check, and it's a bit it's an issue for us if we want to have an estimate of this barycenter, that this set of barycenter is not unique. Okay, so one key property that these barycenters have here in this example is that these barycenters are midpoint to x0 and x1, or x0 and x1. So this is what is written here. Whenever I take the distance from x0 to b star, so this is this arc length distance here, it's the same as the one here, and it's twice, so it's half the one that I have from x0 to x1. Okay, and this property, which is like the existence of midpoint, the point that is in the middle between x0 and x1, is what makes a complete metric space a geodesic space. Okay, and I introduced the notion of geodesic space because it's a notion of metric space that has a bit more structure than the metric space, and that will have enough structure for us to say some interesting thing. And in particular, it's something that the Wasserstein space that I will introduce a bit later. It's a property that the Wasserstein space has. So a complete metric space is geodesic if for every 2 points it has midpoint. And when we think of geodesic, we think of shortest path between 2 points, such that the length is exactly the distance between the 2 endpoints. And why am I defining this with midpoints? And well, because it's easier and it's actually the same thing. So one way to see this is if I want to look at the shortest path between these 2 points here, the 2 points I have here, then I take the midpoint, which is the one in blue here. And if I repeat this operation several times, and I have 2 midpoints for this for every 2 points that 2 consecutive points that I take in my drawing here. And if I repeat this operation indefinitely, then I see that a path appear, and at the limit I indeed have a path. And the length of this path that appears in the limit, and I can take the limit because I have a complete space, complete metric space. This gives me the shortest path that I will call the geodesic. Between the 2 endpoints. Okay, so geodesic spaces have a certain structure that makes them more specific, more particular than metric spaces. So they are including in the set of all metric spaces, but they are more loose. They don't have to be as smooth as Riemannian manifolds. And more important, another thing that is important in our case is that Riemannian manifolds are by design finite dimensional, and the geodesic space do not need to be. So in that sense, geodesic spaces lie between Riemannian manifold and metric spaces. Okay, so now we go to the Wasserstein space, which will be the space we're interested in. So the Wasserstein space is a space of probability measures, so that the second order moment is finite. And it's defined as follows: whenever I have two measures, mu0 and mu1, two probability measures on RD, then I define the distance, the square distance here, as the infimum of the average square distance between mu0 and mu1 with respect to gamma, where here gamma, so the average distance between x0 and x1, where x0 and x1 follows gamma, and gamma belongs to the space of measures on the product space RD times RD, such that the first marginal, so this is a constraint on first and second marginal. Okay, so I look at all the couplings so that this two marginal constraints are satisfied. We know that this minimum is achieved by some couplings that I will denote by gamma opt for gamma optimal. And we know that whenever I have a coupling that realizes this optimal coupling, x0 and x1, there's some random variables that are drawn from this optimal coupling, then I can compute the average between x0 and x1 on my underlying space. So here it's what I have here. I have my 2 points x0 and x1, and I go along these 2 points and I obtain my xt here. And when I look at the distribution of this xt, I have mu t, and mu t is exactly the geodesic between mu0 and mu1. So this is indeed showing that the Wasserstein space is a geodesic space. So now I want to understand a bit what does this space look like to understand how the mean or the average behave, or the barycenter behave. So the Wasserstein space that we just seen is a geodesic space. Then it has some curvature properties. So the curvature I'm talking about here are the one in the Alexandrov sense. So it means that I'm just not going to give a precise definition, but it means that whenever I'm flat, my triangle are the same as the one on the Euclidean space. And whenever I'm positively curved, the triangles are fatter than on the Euclidean space. And when I have negative curves, they are called thinner. Okay, so whenever my underlying space RD is of dimension 1, so when d equal 1, then the curvature is 0. I'm upper and lower bounded by curvature 0. And whenever the dimensions start to increase and I'm above dimension 2, then I have a positive curvature. And the typical example of a positively constant curvature is a sphere. So that's why I will keep drawing examples on the sphere. And since it is positively curved, the geodesics are not unique in general, and therefore the barycenters will not be unique. And it is infinitely dimensional. Okay, so now that I've defined this, the set on which we will, the space on which we will work, I will talk about the empirical barycenter. So this is a joint work with, so it's several papers. It's a joint work with Adil Haidar and Quentin Paris, Philippe who's here, and Austin who's also here. And yeah, so we'll talk about the empirical barycenter. So whenever I have a measure P, I can draw my random variables according to this measure, and I have a sample Pn, so a sample x1, xn, and from this sample I can make an empirical measure, and from this empirical measure I can define my barycenter, and I have my empirical barycenter Bn, and whenever I have my theoretical measure P, I can define my barycenter B star. And the question that a statistician would ask is, when do Bn converge to B star? So it happens that outside of the scope of the empirical barycenter, whenever a measure Pn converges to P, then its barycenter Bn converges to B star. So we know that we have this law of large number in metric spaces, or in, sorry, Wasserstein spaces. This is for Wasserstein. For the Wasserstein space. The interesting question here is, at what rate of convergence do we have that? So to understand the rate of convergence of this, we're going to look at what's happening in the Hilbert space, where we know that the rate of convergence is 1/n. And
so Thibaut, can I ask you a quick clarification? Yes. Sorry. So here, so you say Pn is empirical measure on the space of measures?
Yes.
Can you explain again what was the motivation? Like how do I get such situations?
So when I want to look at the average of the barycenter of, let's say I have 10 measures, and I want to look at the barycenter of these 10 measures. This is
but I mean, where in the real life this question occurs? That's what I'm trying to understand.
Okay, so for example, if so the faces that I showed at the beginning, the faces are images, and images can be seen as measures. So whenever I want to take a combination of images that is not the L2 combination, when I want to take into account the shape of the measures or the images that I want to mix, then this is where you have this kind of thing. But there are other situations, like for example, in fairness, we have a paper with Philippe and Jean-Michel where fairness appears when you want to mix measures to take it to transform an algorithm that is unfair into a fair one. You have to mix measures according to the barycenter of these two measures or these several measures.
Okay, but for images, I mean, you meant, so I represent an image as what? As a distribution over pixels? Like
yeah, so for example, a black and white image, you can see it as density, how black it is how dense the measure is at this point.
Okay, so you normalize the integral to 1 for all images. Okay, interesting. All right, thanks.
So yeah, in the Hilbert space, I can my empirical barycenter has the closed form of being 1/n of the xi, and my b star is the expectation of x. So whenever I'm in this setting, I can do this simple computation. I have my average square distance between my empirical barycenter and the true one that can be written as this. Then thanks to the linear or like the linear property of the norm, I can take the 1n squared outside, and then by using the scalar product, so the Hilbert structure and the independence of the sample, then I obtain this last equality, which tells me that the average square, the expected square distance between my empirical barycenter and the true one is of order 1/n. This proof relies heavily on the Hilbert structure of my space, okay, both through the norm and through the fact that when I expand this square, then I have a scalar products. What we'll do is we want to do the same thing with our curved space. And to do that, we want to have a good approximation of our space by a Hilbert structure, by a Hilbert space. And the way to do that is exactly what tangent spaces are doing, which are locally approximating geodesic spaces, or locally approximating my curved space. So what is a tangent space? So a tangent space is a space that you put on your sphere, in the image you have, which is my drawing here. So I have my point B star that is on the sphere, and I want to put a tangent plane, so a flat plane on top of it that is touching my sphere at the point B star. And then I have to define what are vectors in this space. So I want to, whenever I have a point X here, I want to define a point that goes, I want to define a corresponding point in my tangent space. And the way I will do that is I will take the geodesics that starts from B star and goes to X. So this is the geodesic I drew here. And for every geodesic, it will give me a direction in which I have to go to reach X. And this direction will be defining a tangent vector. So every tangent vector is a direction in which I go in order, direction from which I go in B star, from B star. Okay, so if I
so Thibaut, in this case, you just reduced to a finite dimensional question, right, in n dimensions. right? Because you're only interested in the section of tangent space, right?
No, I'm still infinite dimensional because my tangent space in the case of Wasserstein will be a Hilbert space.
Right, but you only care about n directions.
For the empirical barycenter, you mean?
Yeah, am I wrong about this, or do you? Because then it just becomes right. So you have a Riemannian metric on a flat n-dimensional space. You're trying to compute barycenter, right? Okay, that would be I think an interesting algorithmic question, but it's probably easier than the regional, right? Anyways, yeah.
The thing here is like now I'm on Bn, so B star. So I have to know B star in order to do that. So for now it's for the computation for the analysis that I will do that. I will take the tangent plane at B star, but you have to take the tangent plane at some point. So if you have your sample Bn, so sample x1 xn, you don't know where is B star, so you cannot put yourself in the tangent space at B star. And then where do you put your tangent plane is maybe it will become more clear why we choose B star here. But yeah, the vectors, we will have a finite set of vector, but the tangent space is still infinite dimensional.
Okay, and you say you have to leave the span of the. Okay, I guess because the metric is not flat, right? Okay, yeah, all right, cool.
So yeah, so whenever I have a point x, I can define a logarithmic. So I can define my logarithmic map, which is sending every point on my sphere onto the tangent space. And how do you do that? You take a direction, a geodesic that gives you a direction in the tangent plane, and you run along this direction for the same time that you did on the underlying space. Okay, so I have another drawing here. I have 2 points x and b, and to define log x, I look at this direction and I run the same amount of time. So I have this length and this length are the same, just like I have this length and this length are the same. And we can see that on my sphere, I have this property that whenever I look at the distance on the tangent plane between the two vectors through my log map, it's greater than the one that is in the underlying space. Okay, this is a property actually that is true on the sphere and true on every positively curved space. And to make things more easy and to exaggerate or to be reminded of the fact that the tangent space is a Hilbert space, I will denote this by x minus b indexed by b star to be reminded that it's in the tangent space of b star, that is square also. Okay, so this is not just a notation to say that I will look at x and b in the tangent space at b star. Okay, we know from metric geometry that the difference between these two things, that is positive, is of order d squared b of b star when b tends to b star. Okay, so one of my 2 points here, so when my point here b here move towards b star, these two distance, so the one in light green and the one is darker green here, becomes the same. And the difference between these two distances is of order distance b to b star. Okay, and because of this, I will be able to capture a bit the difference between my tangent space and my underlying space by looking at this difference. We normalize by this square distance between b and b star. And to make the formulas I will get later a bit prettier, I will not look at this ratio directly, but at 1 minus this ratio. Okay, so let's look at what this gives. On a Hilbert space, the tangent space and the underlying space are the same. So this quantity is equal to 1 all the time. When I'm on a positively curved space, as I said, this quantity here is positive. So 1 minus the positive quantity, this will give me something that is below 1, less than 1. And for negatively curved space, I will have the opposite. This will be greater than 1. Okay, so why do we care about this quantity here? So as I was saying, it's capturing how close the underlying space is to be a Hilbert space. And it's actually can be more precise. And we have what we call a variance equality, which is saying that the excess of variance we have here. So remember that this is what I want to minimize to find my barycenter. this is its value at the minimum. And here is the distance of B and B star, which is the two, like B star is my true barycenter and B will be used for Bn, so my empirical barycenter. And this is multiplied by this integrated coefficient. So this coefficient here is, I forgot to mention it, we call hugging coefficient because it takes into account how much the tangent space is hugging the underlying space. And thanks to this equality, we can define a variance inequality, saying that when this integrated hugging coefficient is lower bounded, which is equivalent to have this kind of property. Okay, so why do we care about this kind of property? This kind of property is saying that around its minimum, my variance functional is behaving like a quadratic function. So basically, it's a strongly concave property of the variance function at the minimum. And this is a kind of properties that we need for empirical process using empirical processes technique. And applying this classical empirical process technique, we can obtain rates of convergence that are the following. Whenever my underlying space is a finite dimensional one, if I have a variance inequality, so the one that I just described above, then I have a rate of convergence of the empirical barycenter to the true one at a rate of 1/n. Otherwise, it depends on the underlying dimension. This rate of convergence are probably not optimal. And to overcome this, we will try to work differently and try to work directly with the tangent space. So how do we work with the tangent space? Well, remember that we had this inequality that is the one that that holds pointwise that I just integrated. And I can write the last integral as an integral in the tangent space. So here is I use my log map to push forward my measure P onto the tangent space. And this is the distance between a point Y that is drawn from, yeah, maybe I shouldn't write it like this, but with, yeah, whatever. So which is drawn from the tangent space with my measure log P, push forward of P through log. And thanks to that, I can define, I can see that my, sorry, I'm going to move this a bit in the middle. So thanks to that, I can see that V star is also the barycenter of this push forward measure. How do I see that? Well, this is the sigma P that I want to minimize. This is the one that I would minimize in the tangent space. So this is the one I minimize in the tangent space. And I know that when B is equal to B star, these two distances are equal because this is by definition of the log map, these two distances are equal. So when this one is minimized, it's minimized at B star. And this is when this is equal to also this one log P at B star. And so with the same minimum. However, for the empirical measure, it might not be the same minimum. So it gives me another barycenter, another empirical barycenter, the one that is of the push forward of my measure Pn through the log map. Now, suppose that I have a lower bound on my hugging coefficient, saying that my curvature is controlled. Then using the variance equality and some basic algebra, I can arrive to this equality. So let me pass this equality a bit. So I know that whenever I'm on a flat space, so on a Hilbert space, this quantity is equal to 1, and this quantity is equal to 1. Okay, so this whole quantity is equal to 2. And here I have my distance again, xn minus x when I'm on a Hilbert space. And here, whenever I'm on a Hilbert space also, Bn star is equal to Bn because the log map does not change anything. It's the identity map. And here I also end up with my Bn minus B squared. So this is just a way to like a sanity check of this equality. And from this equality, which is also again just some basic algebra, I can apply here, I can apply my lower bound. So I know that this is lower bounded by K, this part. This, because of my variance equality on Pn, I know that this is always positive. And here I can apply Cauchy-Schwarz, and I have that this is Bn star minus B star. So this is my scalar product on the tangent space. And I obtain this thing. Now I can simplify this part and the square that I have here. And then using the fact that in this I have the empirical barycenter in a Hilbert space and its distance to the true barycenter, then I know that if I look at the expectation of this squared, this is equal to sigma over n, sigma square over n. And from that, we can obtain this rate of convergence, that whenever I have a uniform bound on the Hugging coefficient, then I have a rate of convergence that is lower bounded, upper bounded, sorry, by 1 over n, where my lower bound here appears here. Okay, so now the question is, when do this variance inequality are satisfied? So first we will try to inspect non-uniqueness of this. Sorry, we know that variance inequalities imply uniqueness. So to understand why they are not realized, to understand when they are realized, we're going to look at non-uniqueness. So first, we go back to our example in the sphere. Whenever I have my 2 points, x0 and x1 that are north and south pole, I know that everything on the equator is a barycenter. So this is a case of non-uniqueness. One thing that I can do is that I can pull these 2 points, x1 and x0, toward B star. And from that, I have a new measure that is on x minus 0, x0 minus and x1 minus. And since these 2 points are closer to B stars, then I obtain barycenter that becomes unique. So this is interesting. This is the first observation. And when I do the opposite, when I pull them away from, push them away from B star, then I go on the other side of my sphere, and then the B star is no longer a barycenter. So it seems that the non-uniqueness appears at the limit at when I push away from the barycenter my points. And there is actually a way to quantify, like this is actually a good way to see to obtain the variance inequalities. And it goes as the following. If I, so this, suppose I'm on a positively curved space, so just like the sphere, and I have a measure P with barycenter B star. If I push away from B star all my points with a factor 1 plus lambda, so this is what this equality is doing. So I put this into quotes because this addition is not well defined in general, but it's the notion of geodesic. I extend my geodesic that starts from B star toward X. And this gives me a new measure, this law of X plus. And if X plus satisfies, if X plus has a barycenter B star, keep the same barycenter B stars, and P satisfies a variance inequality with a constant that is lambda 1 over 1 plus lambda. So lambda over 1 plus lambda. Okay, so in a drawing, what I'm doing is I have my points in blue here, my 4 points here. Then I push them away from the barycenter B star, and I obtain my points X plus. I push them away by a factor 1 plus lambda. And this 1 plus lambda, or this lambda, gives me the variance inequality with constant lambda over 1 plus lambda. And I can see that if I'm on a Hilbert space, I can push them until infinity, and then my k-variance inequality becomes a 1 variance inequality here. So how to check extendability on the Wasserstein space? Well, with Bernoulli's to Bernoulli's theorem, it's pretty simple. So Bernoulli's theorem is stating that whenever I'm reaching the optimal in my Wasserstein distance, there exists a function phi such that I can push forward x0 to x1 with the gradient of this convex function and be my optimal transport. So this is if and only if, whenever I have this condition of my on my first measure. This grad phi is called the Bernoulli's map, and phi is called the counter-Witch potential. And I will use this notation. So I'm a little bit behind, so I'm gonna skip the details of this computations here. But basically what we can see is that if I push forward my underlying measures, my underlying points, then I can see that for this extension to be a geodesic, I need that psi which is equal to 1 plus lambda phi, which is my optimal map between x0 and x1, plus say minus lambda over 2 square norm here. I need this function to be convex. And this psi to be convex is equivalent to 1 over lambda psi to be convex. And this is equivalent to psi being lambda 1 over lambda strongly convex. Okay, my definition of strong convexity being when I remove the square norm by a factor lambda, then I stay convex. And using this little proof, we can check that a geodesic between two measures mu0 and mu1 is extendable by a factor 1 plus lambda if and only if its associated convergence potential is strongly convex. How do we find that in Wasserstein spaces? So what does this imply for variance inequalities? So this is requires a little bit of extra work, but in a paper by Sino, Tyler, Philippe, and Austin, they proved that if the support, so they don't state it exactly like this, but basically it says that if the support of my barycenter is, so if my barycenter is absolutely continuous with respect to lambda, and the support is the whole space RD, then my if all convergence potentials are strongly convex with a constant that can depend on the measure mu, the convergence potential from the barycenter to the points in the support of mu, then I satisfy a variance inequality with a constant k that is the average of these strong convexity parameters. Okay, so the takeaways for this part of the talks are a variance inequality imply slow rates of convergence of the empirical barycenter. A variance inequality is equivalent to having a lower bound on the hugging coefficient. And whenever I have a strong lower bound on the hugging coefficient, like a uniform lower bound on the hugging coefficient, then I have fast rate of convergence. And geodesic extendability imply essentially variance inequality. And geodesic extendability in the Wasserstein space is equivalent to strong convexity of convergence potentials. Okay, so now I arrive to my second part of the talk, which was actually the original title, which is sampling from Wasserstein barycenters. So maybe I can make a pause if somebody asks a question for the first part, or maybe keep the question for the end. Okay, so I wait for the end. So the second part is sampling from the Wasserstein barycenter. So this is a joint work with Chieb Dalouche, Jacques Landrat, and Magali Tourneuse that are in Central Marseille. And the point is we want to compute this barycenter. So we have this notion of barycenter that is defined on the Wasserstein space. So it's giving us a measure as a result, and we want to compute this measure. So the standard approach is to discretize the measures on P and so the mu I from, so let's imagine that we have mu I, P that is, sorry, sum of lambda I Dirac masses on mu I. I will discretize my mu i's, and by doing so, I can compute the barycenter. So that a lot of work in this direction. So here I copied first pages of Google Scholar that answer to computation of the Wasserstein barycenter. However, there is one bottleneck in this approach. So not all these papers are doing exactly the same discretization, but they're mostly considering discretization in that way. And one bottleneck is a result by Jason and Henrik. They're saying that it's NP hard to compute this barycenter if we take into account the dimension. So there are things that are polynomial time. So algorithms that are polynomial in the discretization n, in the number of measures k, And so this is just the bit complexity. But whenever we have to take into account the dimension, this becomes NP hard. So the goal is, the hope is that whenever we change a bit the framework, and instead of minimizing P, we look at a situation when we have access to, let's say, the gradient of the potential of the mu i's, like we have in the sampling situation, most of the sampling situation, then in this case, we will not have this curse of dimensionality. So let's look at what we do, what people do in sampling method. What are the sampling method? So one of the most studied one is a discretization of the Langevin process. The method is called the ULA, for unadjusted Langevin algorithm. And it works as follows. It starts by looking at this stochastic equation, stochastic differential equation, which is called the Langevin process. So I look at a measure mu that is given by exponential minus v, and v will be called the potential of the measure. And I take a stochastic process that satisfies this equation. So this txt is the gradient of my potential dt minus the gradient of my potential dt plus some Brownian motion. And there is an important result by Jordan, Kinara, and Otto that is referred to as the JKO scheme, that says that the distribution of xt that I will wrote here as nu t is a gradient flow of the KL convergence in the Wasserstein space. So in order to be able to understand what this means, we're going to have to define what is a gradient in the Wasserstein space. And to define the gradient in the Wasserstein space, we need to talk about tangent vectors in the Wasserstein space. So as we said earlier, a tangent vector is the direction of a geodesic. So I draw my same drawing here for the on the sphere, thinking of the sphere as my Wasserstein space. And what are geodesic in Wasserstein space? Well, we said that geodesic is I have to optimally couple 2 points x0 and x1 and interpolate them. And once I have this interpolation of my coupled measures, then I look at the distribution of this xt, and this gives me the geodesic that starts at mu0 and go in the direction of mu1. We know that by Bernier's theorem that x1 is the gradient of a convex function. So if I look at the derivative of x at 0, I have my x0 dot, which can compute and is my grad phi of x f0 minus x0. And this is a grad psi of some x0, where psi is written here. And this is giving me a way to move my x0 in a direction so that I go from my mu0, my distribution mu0, to a mu delta, for small delta. And in that sense, I can understand that whenever I want to go from a direction from mu0 to mu1, but it gives me a direction in which I want to move. This direction is well defined by this grad psi, and grad psi is a vector field. So I have drawn here points from my mu0. Here are the points for my mu1, and this vector field is telling me how to push my my points that are in the support of mu0, so my random variables drawn from mu0, in order to get closer to mu1 in an optimal way, because I'm in the optimal transport space that is Wasserstein space. So my grad of c is a vector. My grad of c is a vector field, and this will be our tangent vector. So a tangent vector in the Wasserstein space is a vector field on RD, the underlying space. And now I want to reverse engineering what JKO is saying, so that the Langevin process is the gradient flow of so the distribution of the Langevin process is a gradient flow of the KL. So I will look at the distribution that of mu t and see how it is impacted by grad phi. So it's easy to check that. So I just rewrote here my my xt, what xt is following. So this is giving me the distribution mu t, and it's easy to check that it satisfies this equation at 0. Okay, so the derivative of mu t at time 0 is minus the divergence of mu 0 times the gradient of psi. So this is where my psi appear and my actual distribution appear. Okay, and this is telling me how I should move my particles in order to get from x0 x naught to x delta for small delta. So if we go back to Langevin, we can check that it is known that Langevin, the measure of so it's the distribution of xt when xt satisfies Langevin that we called nut satisfies Fokker-Planck equation. And I rewrote here what is Fokker-Planck equation. And so if we reverse engineering what JKO did, then we can identify that the Wasserstein gradient of the KL is exactly the grad log of nu over mu. Okay, and this is telling us how we should move our points optimally in order to follow this gradient flow, our data point, our sample xt. Okay, so one might observe here that this equation for xt is not the Langevin process, so it's completely different. And the reason is here xt has the same distribution, but it's not evolving in the same way. However, we cannot use this directly because we don't have knowledge of nut, which is the distribution of the points at time t. However, there is a trick, kernel trick, that has been used in that was introduced by Liu and Wang, and that is called Stein variational gradient descent, or short SVGD for short. And there is another trick that has been developed in a paper with Sino, Chen, Taylor, and Philippe, that we call low GD. I will not mention here. I will talk about SVGD. So I will briefly talk about it because I want to arrive to the actual algorithm for sampling. So in order to compute this unknown nut, I will change this gradient into a kernel version of this gradient. So I have a kernel here that take a measure mu and is applied to a function f. And I will use this kernel applied to some ut, and I will apply it to my gradient. And it's easy to check that with some like developing my log here into a sum, and by applying some integration by parts, I can obtain this formulation for my kernelized version of my gradient. And what is good about this formulation is that here I'm integrating things with respect to mut. And using that, I can replace mut by the empirical distribution of my particles that are evolving. And using this kernel trick, I can compute an approximation of this gradient flow of the KL. Okay, and this gives me this interactical particle system that allows me to have an evolution of my particles that is basically the kernelized gradient flow of KL. Okay, so how do we use that? We want a sample from the Wasserstein barycenter. So we want to find a functional from which whenever I look at the gradient flow, I can arrive to the barycenter. Okay, so the first thing that comes in mind is say, oh, I want to minimize my variance functional. So I will look at the gradient flow of this variance functional. Unfortunately, this variance functional has a gradient that is a bit difficult to compute. So we will look at another situation, another problem, another formulation of the problem. And the one formulation we will look at is the multi-marginal formulation, which was introduced by again Carlier, and which says the following. So I'm going to skip this little detail, this little introduction. In order to achieve this minimum of my variance here, I can look at the following multi-marginal problem. I'm going to look at the infimum over all possible coupling of all my marginals mu1 and mu_n of the integral of this cost function, that is the average square distance of the points that are drawn from this coupling that I integrate with respect to this coupling. And the useful part for us here is that whenever I have B star my solution of this, then it can be computed by looking at the push forward through the application, the barycenter application on RD, which is X bar, that from X gives X bar, of gamma opt, and gamma opt is the one that minimize this multi-marginal transport. So if I obtain the solution of this multi-marginal transport, I can compute the barycenter. So what I will do, so here was an example, but I'm running out of time, so I'm going to skip this. what I can do is I'm going to minimize, I'm going to look at the minimum of this function, f alpha, which is here, this is the multi-marginal problem I have, but I cannot look at the flow gradient with constrained marginals. So instead of doing this, I'm going to add some penalization for my marginals constraint. So I will look at the following function, multi-marginal plus penalization parameter alpha times my constraint on my marginals. And this I know how to sample from. I just look at the flow gradient of this that I canalize for the part of the KL. And I obtain, so it's a long line here, but this is just what I did earlier. So this is svgd flow gradient. And here, this is just the gradient of my first part here. So I'm just gonna end this presentation with some simulation. So in this example, we drew first in green here, this is a point that are drawn from two uniform measures in this box. And then I applied the gradient and increased, okay, I still have 5 minutes. So I have, you start with the green points here and you apply your flow gradient, and this will move all your particle according to this. The two measures that we took were on R, so this is the two measures, two Gaussians, that one was centered in -2 and the one was centered is in 6. In this example, we have a sample of 200 points and we run the iteration for 300, we had a 320 iteration. What we can see here is like we have some front here that change suddenly the behavior. This is every time we increase the alpha. So what we did is we ran the algorithm for a little while with a certain alpha, and when it was starting to get stuck, we increased the alpha, and the alpha is again the penalization on the constraint here. So with a low alpha, we are allowed to change our marginals in order to have a better value for the multi-marginal problem. And by increasing alpha, we enforce more and more to have the right marginals. So here is another example where we started by taking points uniformly on this square. And we had a different link between the two measures. So the first one was a Gaussian, and the second one was a arctan, the push forward of arctan, mu1 through arctangent. And our sample size was 200 and the iteration was 220. And we see that in gold here, we have the limit where the optimal transport. So here's the arctan between the two measures. And this is where our weight points are gathering. And sorry, I forgot to mention in the above graphic, I have two measures. The first one is this one, which is my arctan measure. The second one is, or maybe the other one, sorry. The second one is this one, the arctan push forward, and this one is my Gaussian. And the barycenter is computed in two ways. So since it's low dimensional, we could use other techniques. And in blue, we have our estimated density thanks to our sampling. And in black, we have the original one. Okay, this is another simulation with 3 measures on R, with one being the Gaussian, or 2 being Gaussians, and 1 being also the push forward through arctangent. And maybe a more interesting one is the one on two-dimensional measures. So we have 3 Gaussians here, and we're looking at the sampling from the barycenter of these 3 Gaussians. And again, we see that we start with points that are here. And again, we see that after changing the value of alpha, increasing the value of alpha, they move until they converge where they are supposed to go. Unfortunately, the theoretical results are a bit sparse for now. So I'm just going to mention one. So we call that f alpha is this function that we want to minimize. That is the multi-marginal plus some constraint on the marginals that are through a penalization term. And looking at this functional and trying to minimize it is a good idea, because whenever, so my measure P, that is this finite set So there's a finite mix of measure. If it satisfies a k-variance inequality, and each mu I satisfy a log stable life inequality, then when I'm epsilon close for an alpha fixed, when I'm epsilon close to the minimum, then the barycenter with the Wasserstein distance between the barycenter it gives me and the optimal one is upper bounded by epsilon plus this constant divided by square root of alpha. Well, this constant here depends only on sigma square and the constant of the log stable life inequality. And k here from my variance inequality appears here. Okay, so I'm gonna stop here because I think I'm out of time.